So what is multiple regression? A multiple regression model, or MRM, is a model for association in the population between multiple explanatory variables and a response. So you have one dependent variable or response variable, and you don't have only one explanatory or input variable. You have more than one. It can be at least 2, 3, 4. So when you have multiple input, multiple explanatory variables or independent variables, considering association of these explanatory variables to one response variable is called multiple regression model. So basically, what's the difference between simple regression and multiple regression model? Simple regression, you have a one-on-one analysis of relation. In multiple regression, you have multiple explanatory variables associated with one response variable. What is K in representing in this book? The number of explanatory variables we use in our multiple regression is represented by K. If K is 1, of course, you have one IV, one explanatory, and that's a simple regression model. So you remember that a simple regression model, when you calculated and got your slope and intercept, you would have the first part of this part from y equals to, or y hat equals to beta 0 plus beta 1 x1. That would be for simple regression. The multiple regression, you have more factors involved, right? So you also have beta 2 x2 for your second variable, second explanatory, third, fourth, up to K explanatory variable, and each of these have a slope, right? Slope associated. And of course, if this estimation, we consider the residuals is added to both sides, and y will be accurate now, and epsilon represents errors or residuals of your regression model. However, you can see that residuals are supposed to follow. That means it follows normal probability distribution with expected value, an average of 0, and the variance jumped here. Variance is the variance of the residuals, which means we want residuals to have similar variances, okay, of sigma squared. Also, we want to make sure that these residuals are independent, right? So we want to make sure errors or residuals are independent, have equal variances, and are normally distributed around the regression equation. So this is the example that we have. We're going to cover today, and let's look at what variables we have. Response variable, sales. So we want to increase sales, we want to manage sales. Chain women apparel, and annually in dollars per square foot of retail space. And there are two explanatory variables, or input variables, or independent variables: median household income, or in a very short form, we say income in that area in $1,000. So if we say 70 means $70,000, right? And number of competing apparel stores in the same mall. So of course you always have competitors, right? These competitors reduce your sales because number of customers will be divided into different stores. As a result, the more competitors you have, that reduces your sale, right? It's a negative effect on your sales. So these are the two factors we're considering. Are there other factors? Of course, yes. We're not considering them for this example at this point. So to make sure that we understand this example well, I'm actually sharing with you the data And to find the data, all you have to do is to go to Canvas. So all you have to do is to go to Canvas and go to Files, go to your data folder and find 23, the mol data, okay? All right, so I recommend you can open your JMP data and see this data right there. So you can see we have sales, we have the income in $1,000, we have the competitors, how many competitors in each location we have, and mall visits, right, per month. Okay, so as you learned before earlier from last lecture, when steps of checking association between multiple inputs and one response, or multiple explanatory variables and one response, the best to start the analysis is going to analyze multivariate methods, multivariate, analyze multivariate method, multivariate, and this is the starting point. What are we looking for here? We're looking for a scatter plot matrix and correlation matrix. So when you have multiple explanatory variables, you need to see all the associations at the same time. So sales is my response, and also any other explanatory variable I'm considering, these two, they all go, look, they all go to the same box. They all go to Y columns under multivariate and correlation. Click OK. So what you see here is correlation matrix is right there, and your scatter plot matrix is right here. So you don't have one scatter plot, you have multiple, and each of these are showing association or correlation between 2 by 2 of these variables. So if you pay attention, you can see that this is your diagonal of the matrix. Below the diagonal and on top of the diagonal are actually the same things, okay? So we can just look at one of them. Now, looking at correlations, I can see that under sales, the first column, sales by sales is 1. Of course, those that are the same, association to itself is 1. So ignore those ones. Never use those ones in your reports, because that's sales to sales, income to income, competitor to competitor, right? So which one should I look at? First column, income correlation between income and sales is 0.7. It's a strong relation. Is that significant? Correlation probability. So I clicked on the red triangle, the second one, correlation probability. That shows if these correlations are significant or not. I know that this is a strong relation association, but is it significant? Yes. P-value is less than 0.05, right? How about competitors to sale? Competitors to sale. This is 1-on-1. Is that significant? It's a very weak relation. Is that significant? No, it's more than 0.05. How about the scatter plots? I can see that there is a linear association between sales and income. And look, any of these two, this one or that one. Sales and income, are they linearly associated? Yes. How about sales and competitors? Where there is, it's like a circle, it's not perfectly linear, right? So we will talk about that later. How about the association between income and competitors? So income, competitors, you can see that the higher the income, the higher the number of competitors, also higher the variation of competitors. So why is that? It's because when your customers, clients, the area in average or median of income of people in the area that you're buying the store. Their income increase because more rich people are there. Of course, more companies and more stores are being opened because they all want to make profit, right? They all want to sell. When they know people have money in their hands, they want to open stores and have sales. So as a result, more income is associated with more competitors, right? So that's the first part, which is correlation matrix. All right, so that was the first part of our analysis. So let's move on and let's check our slides too. Do we have what we covered? Yes, scatter plot matrix. And you can see that it's the same scatter plot we had in our results. And please read the book on this topic. You already have learned the topic using this data. You just need to one time read the book and make sure you understand the analysis. So, and that's your correlation matrix, right? That's your correlation matrix. 0.7 was significant. 0.06 was not significant. How about the 0.4? What is the 0.4? 0.4 is representing the correlation between income and competitors. Checking back on our results here, is the 0.47 significant? Yes. The p-value is less than 0.05. So there is a significant association between income and competitors, okay? And is that strong? No, that is moderate because it's close to 0.5. So when your correlation value is close to 0.5, that's a moderate relation or association. Is that significant? Yes, that's a significant association. Does the scatter plot confirm that? Yes, we have approximately a linear association between income and competitors right there. Okay, next is the regression model. As I told you before, you expect to have a regression model as y equals to intercept plus slope of the first beta 1 x1 plus beta 2 x2. So let's look at our data. And we want to analyze fit model. Sales is response, goes to response. And income and competitors together, these two together, they go to construct model effect. Right? So that's your explanatory, that's your response. All right, so let's click run. So previously when I explained multiple regression, if you remember, I did use the minimal report. And now I'm going to explain some of these results here, so I won't use the minimal report. Okay, looking at the R-square first, 0.59, 59.4 or 59.5% of the variation in sales is explained by, so previously in simple regression model, we said by the explanatory variable, by one variable. But here we have two variables. So this R-square, in fact, represents almost the same thing, but it's not each of these explanatory variables, but the combination of their effects. So income and competitors together, they actually explain 59.5% of variation in sales. So the variation in income and competitors, right? The combination of these two, their variation explains about 59.5% of variation in sales. So variation in sales is actually influenced by the variation in income and competitors. Let's see, what else do we have? R-square adjusted. So R-square adjusted is a little different. You can see that's a little smaller. And why is that? That's because we're considering how many explanatory variables are involved in the calculation of R bar square. There's a formula in the book. You can learn from it and read it. You don't have to memorize the formula. You won't use this formula, but just to know why they're different, because the R bar square or the adjusted R square is actually calculated by considering K, which is number of explanatory variables in our calculation. Okay, so what else do we have? We also have standard error. Standard error of our model, that's standard deviation of these residuals, how far they are from the regression line, right? And then we have number of observations 65. Analysis of variance, I will explain it to you. And also we have the model, right? The intercept, 60.3 plus 7.9 times the income minus 24.16 times the competitors. Let's check that and see if that's correct. 60 is correct. 7.9 times income minus 24 times competitors. Same answer we have here. Okay, so what else can I get here? The analysis of variance uses F-test, right? Like Z-test, like T-test. We also have an F-test. F-test will tell you your regression model as a whole. Is it a significant? Is it creating a regression line fit to data? Is this regression line fit to data in general as a whole? So where do we look at? We look at the p-value of F-test. And you can see that the p-value is less than 0.05. So that's small enough. So it indicates that this model as a whole, including income, competitor, and sales altogether, and the intercept, that's a significant model, right? F value, which is normally questions on, is a question, what's the F value? 45.49, right there. Okay, and see what else we have. So R square and SE, so standard error, I told you what it is. And the amount is not that big, that's good. And you can see that R bar square is known as adjusted R square. It adjusts for both sample size and the model size, K. K is number of your explanatory variables. The residual degree of freedom is, this is important to remember, the residual degree of freedom is n minus k minus 1 and divisor of the standard error for calculating your R bar square or the adjusted R square. So what is a calibration plot? A calibration plot is a scatter plot of the response y on the fitted values of y hat. So what's the difference between y and y hat? Looking back at the data, this is my data, right? The response variable here is sales. These are the actual y's, actual response values. And that's right there. Response, scatter plot of response y. That's your response y. Actually, the dots on the scatter plot versus the values calculated based on the formula, right? So we have a formula here. The question is, if I plug in the same values that we have in here, if I use exactly the same values, same income and same competitors into this formula, do I get these numbers? Do I get the same response? Of course, there will be a difference because this is an estimation, right? The question is how far they are from each other. So to find out how far they are from each other, a calibration plot helps a lot. Because if they are close enough, your scatter plot would look like a linear association. If not, it would be far from linear association. So the R square is the correlation between Y and the Y hat. The tighter the data cluster along diagonal line in the calibration plot, the larger the R square. And the larger the R square, of course, the higher the percentage of variation explained in your response variable. So you can see that there's pretty much a good, here you have estimated sales. That's using the formula, plugging in the numbers into formula and getting values. And here we have the actual sales that we have in our data. Putting them together on a scatter plot, if they are close to each other, that means this line is pretty much giving us similar numbers, right? Not very far from the actual values. And that's a good sign for our model to be correct. All right, so what is the difference between marginal and partial slopes? So let me first explain the marginal slopes. The marginal slope is the slope of explanatory variable or independent variable in a simple regression model. So marginal is simple regression model. However, partial slope is the slope of explanatory variable in a multiple regression model. Why is it partial? It's partial because your sales is not being estimated by just one explanatory variable, but a combination of them, right? So that value is partially explained by x1, partially explained by x2 and x3 and x4 and so on, okay? So that's why we call it a partial slope. How do we get the results from JMP? So going back to data, let's do marginal slope first. For marginal, you need to go to Analyze, Fit Y by X. So if you want to get the marginal, one-on-one, go to Fit Y by X, and do the same you did for multiple regression. Sales, go to Response. These two, they both go to X. So what's going to happen, JMP is going to separately create one simple regression for sales and income, one separate results for sales and competitor, side by side, right? So the first one is the scatter plot for the income and sales. Second one is competitors and sales. Right, so do we get different results from the multiple regression that we just ran? This is a multiple regression. These are the slopes of income and competitor, 7.9, negative 24, right? So we expect to have different results. We expect to have different results. Let's see. So these are 7.9 and 24, but here, let's get the fit line. Fit line. And look, 97 is the intercept now. 6.4 is the slope of the income. The slope of income here is 7.9. Here is 6.4. Why is that? Here, both explanatory variables are associated to sales at the same time, right? They're both in the model. But here, it's separately being affected. R square is, of course, lower. Using one variable, you have you're covering a less portion of variation in sales, which is 50%. And that's your intercept and income. How about the competitors? Red triangle, fit line. Also, you can see 502 is the intercept, 4.6 is the slope, right? Is that a significant model? Competitors? No, it's 0.59. You can see that p-value is not less than 0.05 as a result. So what are these? Marginal slopes. So if the question asks you what are the marginal slopes, you use the fit y by x and use these slopes right there. The 6.4 and 4.6. Okay, how about the partial slope? Partial slope is the multiple regression results. Check the multiple regression results, and that's your parameter estimate results. And slope of income, estimate of income, 7.9 times income, and then negative 24 times competitors. Are they both significant? Yes. What happened? Why competitors by itself, it was not significant, but when it works together with income, combines with income, it becomes significant, right? I told you, because income and competitors, they're somehow associated, and this association helps to change sale, because the higher the income, you have more competitors, you have less sale. So somehow, indirectly, competitors is affecting sales. Okay, so I hope you understand the difference between partial and marginal slope. Next is the results of multiple regression that you just saw it here. As you can see, let me down, and it's the same numbers, right? Same numbers. So standard error for intercept is 49. Standard error for income is 0.8. Standard error for competitors is 6.3. That's correct. T-stat says if income and competitor B1 and B2 are they significant? Are these values significant? Based on the T-stat, 9.5 and 3.7. Absolute value of T-stat has to be 2 or more so that we have a significant slope. Also, it's the same as checking the p-value. So checking p-value or checking T-stat are actually the same. T-stat to be 2 or more, that means your B1 and B2 are significant, or p-value less than 0.05 also means they're significant. And then we have interpreting multiple regression. So the slope of 7.9 of income implies that a store in a location with a higher median household of $10,000 sells on average $79.66 more per square foot than a store in less fluent location with the same number of competitors. How about the B2 or slope of competitors? Negative 24.1 or 0.2 implies that among stores in equally affluent locations, each additional competitor lowers the average sale by $24 per square foot. So each additional competitor will negatively influence your sales by $24.1 per square foot, but higher income in average, right? It actually increases your sales by $7.9 or $79.66 per square foot. So partial and marginal slopes only agree when explanatory variables are uncorrelated. So if explanatory variables are correlated, like this case that we have, and what was the correlation? We checked first, the correlation between the explanatory variables income and competitors was significant, and it was a moderate 0.47. It was a moderate correlation here, right? Independent variables or explanatory variables are supposed to be kind of independent. They're not supposed to be highly correlated. And they're not highly correlated, they're just moderately correlated here, and that's fine, okay? So in this example, they do not agree. For instance, the marginal slope is 4.6. It is positive because more affluent locations tend to draw more competitors. The multiple regression model separates these effects, but SRM does not. A simple regression model does not. And I just showed you that, right? This is your simple regression results. That's the 6.4 and the 4.6 for competitors. And you saw that it's different from the multiple regression results, which was 7.9 and negative 24. And that is because of the correlation between the two explanatory variables. What is a path diagram? So a path diagram, schematic drawing of relationship among the explanatory variables and the response. And what is collinearity? If there is a high correlation, in this case, it was not high, it was a moderate relation between independent variables or explanatory variables, right? So, but if you had a high correlation or very high correlation among explanatory variables, that makes the estimation of multiple regression wrong or unreliable or uninterpretable. So collinearity is high correlation between independent variables or explanatory variables, and it's not good for multiple regression. So we don't want to have collinearity condition in regression model. So you can see here, that's a path diagram for this problem. Income directly has influence on sales. However, competitors or competition or competitors, they don't directly have influence on sale, but through income. So income actually increases or changes competitors, and the competition, higher competition, create a lower sale. And that's how this is explaining to us how this association is happening. And you remember that competition and sales by themselves alone, they don't have significant association. But when income is involved, you can see that through income, we have more competition, and more competition creates less sales. You can see that income has a direct positive effect on sales and an indirect negative effect on sales via the number of competitors. Okay, so now it's a good time to check conditions and conditions of inference. Use the residuals from fitted multiple regression model to check that errors in the model are independent, have equal variance, and follow a normal probability distribution. So we can do that. Okay. Check residuals, plot of residuals versus fitted Y values is not only used to identify outliers and to check similar variances, but also to check dependence. And how do we check dependence? Of course, if there is a pattern in residuals by changing X values or fitted values. So when you change the Y or sales values, are residuals moving toward a certain direction, growing up or reducing? That is considered dependence or having a pattern, right? If that pattern does not exist, they're independent. Plot of residuals versus each explanatory variable. So we will have the plot of residuals versus each explanatory variable, and we use it for verifying the linearity of the relations. So visually estimate the standard error. And what's the standard error? That's the residuals standard deviation, right? Which is less than $75 per square foot. All residuals lie within 150 of horizontal line, and that means we don't have evident pattern. So you can see by increasing sales, moving to the right, we're moving to the right. Are the residuals moving up or down? They're not. Do they have a pattern like moving toward a certain direction, going up or going down? The answer is no. They are randomly moving around, right? Almost everywhere. So we can say that they don't have a pattern, and because they don't have a pattern, they are not dependent, they are independent. Another way to look at this is a residual plot, income, IV1, and residuals. Do you see a pattern here? We don't see a pattern. Do we see variation in our sigma square? No. You can see that is not a problem. How about for competitors? You can see that residuals are nicely and randomly spread around this horizontal line, symmetrically on top and bottom of the line. This plot of residuals versus comparators does not indicate any problem. So we don't have a variation problem, and we don't have, so we have similar variances here and also here, and we don't have any patterns. The other condition we need to check was normality of residuals. And you can use the quantile plot. Quantile plot shows that residuals are pretty much in the range between the upper and lower bound here, and that shows their normal. A perfect normality on quantile plot is all these points should be on that center line. They're not, but they're still between the upper and lower bound, and that satisfies what we just said. So let me just show you on JMP how to get these results really quick. Okay, so we have, there are different ways to do this. One, so do you see here we have the actual by predicted. So the actual by predicted is what we talked about earlier, and that shows that we have a good fit here. And here we have income to residuals of your sales. And we also have comparators to residuals of sales. They show linear relation, linear. So association between comparators and sales is linear according to the residuals, and also same for income. And this plot, let me find that plot. Slide number 15. Slide number 15 is calibration plot, right? You see that it's estimated sales and sales, estimated sales and sales. That's the same thing we have here. Estimated sales, and actual. Estimated sales using the formula and actual sales. Okay, so what else do we have? We want to check residuals as well. So what do we have here? Predicted sales versus the residuals itself. You can see. Do you see a pattern here? By increasing sales, are residuals increasing or decreasing? The answer is no. We can also make this like a box to see that better. Right? They're not having a pattern. Having a pattern, they look like going down together or going up together, or creating a triangle here on reducing or increasing. And that's not happening here. They're spread almost everywhere. So we don't have any pattern here. Remember that all of these plots that we see here, there are many other ways to get these, okay? There you can click on red triangle and get the same results from different options that we have here. But let me really quick show you where to save the residuals. If you want to have actual residual values, go to Save Column and click on Residuals. And you need to look back on your actual data. The residual values will be present on your data set. Residual. So I go back to my data. Look, this column is added. The positive numbers are the points on top of the line. Negative numbers are the points, residual point below the line. And these numbers are actually the difference between predicted values and actual values, 4, 60, and 3, right? So where is how can I calculate the predicted values? That's also easy. Red triangle, save column, predicted formula, prediction formula. So prediction formula. So look, that should be the difference between 490 and 465.8. 490 and 465 should be this 24.70. You can check it yourself. That is what residuals mean, right? Predicted values versus the actual values. That would be the residual values, okay? So let's go back here and see what else we wanted to say. Oh, so checking normality of residuals. So now we have residuals. Can we analyze them using distribution? Yes. Residuals, go to Y columns, analyze distribution, okay? Go to analyze distribution. You have residuals, you can analyze them. One way to analyze them is checking there are many different ways you can do this, right? Histogram, I want it to be vertical bars. And pretty much normal, you have tails almost symmetrical on both sides. That line is the median. Median is supposed to be in the center. If it's center, that would be a perfect normality, but it's not. It's not perfectly normal, but still considered normal. But the book explains using Quantile Plot. So it's normal Quantile Plot. Click on the red triangle, normal Quantile Plot. That plot appears here. And that's the same plot you had it just now in slides. If you check down here, we had it this one. So F-test is a test that explanatory power of the multiple regression model as a whole is being explored. The F statistics is a ratio of sample variance of the fitted value of the variance of the residuals. So F-test, F value can be calculated by R squared divided by 1 minus R squared multiplied by, that's your n minus k. K is n is the sample size, k is number of multiple explanatory variables. And that's how you calculate F. And this is used to test the null hypothesis that your beta 1 and beta 2, in this case, because you have two explanatory, if you have k explanatory variables, that would be all of them to be equal to 0. So that's your hypothesis null hypothesis. The null hypothesis, you reject it if p-value is less than 0.05, right? So what is the null hypothesis here? It's saying your slopes are 0. Looking at our results, are our slopes 0? These are the slopes, 7.9, negative 24. Are these 0? The answer is no. So p-value of F has to be, F test, the p-value has to be less than 0.05, which it is right here. That's your analysis of variance F test. The F value is 45. The p-value is less than 0.05, which means we reject HO, and that means we reject this. That means beta 1 and beta 2 are not 0. They are some values, some significant values. And this is the same as what we got in our results here. Look, you have the 45.49, 45.4940. That's your F value. And p-value less than 0.0001, right there. Sum of the S squares is the same, 421, 286, that's correct. All of them are correct, okay? So the F statistic or F test has a p-value less than 0.0001. We reject HO, income, and competitors together explain a statistically significant variation in set. So what F tests help us to understand is the inference in multiple regression. The multiple regression model as a whole. The whole regression model, is that reliable? Is that working? We reject HO? The answer is yes, because p-value is less than 0.05. So in other words, when you are interpreting these results, you can, for F-test, you can always say, if p-value is less than 0.05, you can say the model fits to the data. The multiple regression model fits to the data, okay? Next is the T statistics we use for, I actually have already explained this. The T stat we use, if there are more than 2 or p-value is less than 0.05, that means these two numbers, 7.9 and negative 24, are significant. They are significantly calculated, okay? But how do you calculate the T value? T0 is for intercept. T1 is for income. T1 is for income, T2 is for competitors. So the B, or the slope, divided by the standard error of the slope. Where is that? Slope divided by the standard error of the slope, B1, 0.8, B2, 6.3, right there. Okay, and these are the same numbers that we just saw right there, but checking p-value is enough. So how about, where do we get the confidence interval of our results? This is the results, right? So you just right click on the parameter estimates, go to column, lower 95, go to column, upper 95, lower and upper 95% confidence level around 7.9 and around -24. So 6 and 9, you can see that 7.9 is between 6 and 9. And the -36 and -11 are actually around -24, okay? And those are the same numbers here, you can see it. So one important thing that I forgot to say, the intercept, p-value of intercept is not significant. Is that a problem? The answer is no. For multiple regression, it's opposite of simple regression. Simple regression, intercept has to be significant. But in multiple regression, because this intercept represents multiple variables, right? So it's coming from multiple variables. So it's not actually explaining what we are expecting to explain. So it doesn't have to be significant. Remember that. So lastly, the prediction intervals. So prediction intervals are actually vertically. Let's look at the regression line here. If we have the regression line, the question is, what would be the margin of error around the prediction value or sales, right? So where and how do we calculate it? Of course, you have learned, when you learn standard deviation, you remember that 2 times standard deviation plus minus average. So this is almost our average estimation of line in average, plus minus 2 times the standard deviation of errors, includes 95% of our observations, right? That's what it actually means. So where do we get these numbers? Really quick, we go to here. Red triangle, save columns, prediction formula. Prediction formula. I've already done that earlier today, so you can see it. Prediction formula. So if a new x and a new y is given to you, in this case, when we say x, we have 2x, x1, x2. If a new value for x1 and x2 is given, we plug them in here, and a sale value is estimated here at the end of our data. So let's see what values are given here. The book, the example in the book has 70,000 income and 3 competitors. Let's calculate this using JMP. So we go to the actual data. We already have the prediction formula down here. For income, it's saying 70,000. So I just type 70 because these are based on $1,000. Press enter. And still nothing because you have 2 IVs. You have 2 explanatory variables. How many competitors? 3. I'm talking down here. 70 and 3 are added. Press enter. You expect to see the value for prediction formula down here. Estimation will be calculated. 54548. 54548. Right there. 54548. That is the estimation for sales. Why we don't have it here? Because we never had this value in our data. So we don't have something similar to it. but we did the calculation. How about the confidence interval y hat plus minus 2 times standard error? Plus minus 2 times standard error, also we can find it from the regression results. Let me really quick show you. Okay, so let me show you really quick here. Go to multiple regression results, red triangle, same place you went earlier. And click on individual confidence limit formula. It will actually create both. You can see that they both were created to the right hand side of your predicted value. Prediction formula, lower 95 around it and upper. So like 659 is between 513 and 799. 466 is between 328. And how far are they from 466? 2 times the standard error. What is the standard error? Right there. Root mean square error, 68.03. That's your standard error, SE. Plus minus 2 times SE, that would give you that value. Now, do we have it for our new values that we just entered? Yes, 70 and 3. That's the estimation of sales. That's the lower 95, that's the upper 95. So do we have the same numbers here? Yes. So using JMP, prediction formula will be this. Plus minus 137, you will get exactly the same numbers we have here. You can calculate it yourself and check the numbers. Let me bring this up and you can see the numbers. Compare the numbers. Okay, 544, 545.48. Plus minus 137.29 will be 682 and 408. But if you check the textbook has a different calculation. It's just a few decimals different. And I just created a Excel file here so show you how that calculation is different. So the book income was 70, competitors was 3. Predicted sales, we just calculated together, 545.48. Standard error 68.03. So if you use the t distribution of 95%, degree of freedom of n minus k minus 1, which is 65 minus 2 minus 1, which is 62, or use the 2 times standard deviation, right? Standard error. So 2 times standard error, 2 times 68, that's 136.06. 2 times the standard error, that's 136.06. So you can see that if you read the book, the actual textbook, on the page that explains this part, the book explains that the 136.06 is correct. The JMP calculates by a little different estimation, which is because of a rounding, just has a few decimals difference, okay? And that's okay, but you need to know both because you need to know how these calculations are done. So you can see the 136 is 2 times the before is here, 2 times standard error. And confidence level up is 545, 1 time minus B5 times before, and 1 time plus. So that's the average plus minus 2 times the standard error. Okay, so those numbers are calculated. Okay, so let me really quick check these. So there's another example here. This example, please read it from the book. It just explains the same things, just a different story, a different example. So I believe that you're good now to work on problems we have on JMP, on MyLab. But one more thing to really quick show you here is these are your results. So I told you what the VIF is. So you want to add the VIF here, right click. That's the VIF. Parameter estimates, right click, column, VIF. If VIF is more than 10, that independent or explanative variables are very highly correlated. You remember I said up here, right here, collinearity. So when we say collinearity, VIF more than 10 or around 10 means there's a high correlation among explanatory variables, and that's not good for multiple regression model. So remember where to get it. Parameter estimates, right click, columns, VIF down here, okay? All right, so you can also check if your residuals are independent or not by going to the red triangle, row diagnostic, Deriving Watson test. And all of those graphs plot actual with the predicted leverage and residuals by predicted, residual by rows. You can click here and they will appear. And Deriving Watson test down here. So if you go down, you can see that all you have to do is to look at this number has to be close to 2. Or if you want to be accurate, check the p-value. P-value is supposed to be more than 0.05. If the p-value of Deriving Watson is more than 0.05, that means residuals are independent. If the p-value of Deriving Watson test is more than 0.05, that means residuals are independent.